Hi, so today I'm going to be looking at what are the different types of programming language. So from your previous studies, you've probably heard of high-level and low-level languages. The low-level languages are, for example, assembly code or even machine code. And the important thing there is for each instruction you give, there is a direct mapping to the instruction that the processor actually carries out. So in assembly language, for example, you give 3-letter acronyms like add and then a value 5, and that value add will map directly to a sequence of ones and noughts that goes through the processor. You can also directly manipulate devices within the hardware and also the values that are stored in memory. The downside of low-level language naturally is that there's a lot more coding involved, because you've got to write every single low-level instruction, and then on top of that, the instructions are specific to a given architecture. So if you write a low-level program for a PC architecture or a certain chipset, it's not going to work on, for example, a mobile phone. They're used principally for programming firmware and device drivers. So firmware contains things like the boot instructions for a device, and a device driver is a bit of software that controls a specific piece of hardware. High-level languages is what you'll be much more familiar with programming in. So Python, C#, SQL, Haskell, they're all high-level programming languages. One instruction in a high-level programming language translates to many instructions in machine code. And as a result, it's much quicker to program in high-level languages. They're written in a format that's very close to English, so they're really easy for you to understand, and all the details of the hardware are actually abstracted from your view. So when you're, for example, assigning a variable, you don't need to think about which specific address in memory this needs to go into. As a result of it being so high level, the code is actually compiled down to the specific architecture of the machine. So if you're programming in, say, C++, there would be a compiler to get it down into a format that's suitable for a mobile phone or an Android device, and equally you'll get a compiler that's suitable to get it onto a Windows machine or onto a Mac. And therefore the code itself is actually portable between different architectures. And high-level code has got all the high-level programming constructs that you're kind of familiar with, like sequence, selection, iteration, subroutines. And also the important thing is it also supports aggregate data types. So for example, like lists or dictionaries, so data types that don't just have a single piece of data in them, but actually have a range of items of data in, are supported by high-level languages. And we use them for making standard client-side applications and web services. So here I've got a little snippet of assembly language, just so that you kind of are aware of what it looks like if you haven't seen it before, and you'll note that it's really different to your kind of Python programming you've done before. You'll see that all of the instructions are encoded as 3-letter acronyms, so that means load whatever's at this location into the accumulator, or maybe even register A into the accumulator, and that's a comment. And then it says store what's in the accumulator at location A, I'd assume. And you'll note that there's no if statements, there's just jumps to specific labels. And you also have these branching commands that basically say if what's stored in the accumulator, which is like the kind of like the register that stores the result of the last operation. There's these instructions that say like branch if that is positive, negative, and so that is how they control the flow of execution within the program. So within high-level languages, however, so we're going to move away from assembly language and low-level. We've got two kind of families. We've got the imperative and the declarative families. So when you think about these two terms, you need to just think about what they mean in English. To give an imperative means to give a sequence of instructions, where to make a declaration is to state what you want done without saying how you'd like it to be done. So imperative programming, the program actually determines the sequence of statements needed to reach a given goal, and that's what you'll be most familiar with. So Java, Python, and C are all imperative languages. They are used in generic applications development. And the other important thing here is that while it seems that you could think, right, there's low level and high level, and then high level can then be imperative or declarative, you shouldn't think of it like that, because low level languages do specify the sequence of instructions and the flow of execution, and therefore they are too imperative. Declarative languages are much more abstracted from the actual hardware, and the programmer doesn't even specify how the program is going to be done. They just specify a sequence of rules or criteria that are present within the problem domain, and then an inference engine goes forward and from these sets of rules and criteria determines which of the declarations are interpreted in which order. So the examples of this are Haskell, F#, and Prolog, and they're generally used in quite specific domains such as data mining or AI or mathematical modeling. Okay, so there are further types of imperative language. So we divided those up into imperative and declarative, and so we're now just going to look at imperative, and I'm going to go through a few progressions of the imperative kind of paradigm. So when I mean paradigm, I mean the way in which we code. So there are kind of like paradigm shifts in coding every 10 to 20 years where we fundamentally change the way that we go about doing things. And over sort of the last 50 years, we've seen a gradual improvement within the imperative paradigm. So imperative programming was good in the 1940s and 50s. However, they had this statement called the go-to statement, which effectively said, if this is the case, then go to this line of code. That's kind of like the labeling that you saw in assembly language. Well, I think it was Dijkstra, a Dutch computer scientist, thought that this was bad and wrong because it led to what we called spaghetti code, where it was quite hard to follow the route that the execution was taking. And so as a result, we introduced things like if statements, loops, subroutines, recursion, and as a result of doing that, the code became much more structured and meant it was easier to debug. And all current imperative programming language you would consider to be structured, probably with the exception of assembly language, which doesn't have those things that I've listed. Procedural programming, on the other hand, it was just a development on from there. So you possibly could imagine having structured programming as in having subroutines, but not necessarily within that having the parameters that go within them. So the subroutines were developed in the 1960s and 70s, and they actually required a change to the underlying programming structure and the actual underlying hardware of the computer. So what they implemented was this thing called the call stack, and so what it did is it remembered the line of code that it was at when a procedure was called, and then if a procedure called a procedure within that, it would place another return address onto the stack. And this call stack also includes all of the variables that are associated with a given procedural function. As a result, you can use variables both locally and globally within your program, and the variables that are declared locally after the procedure or function is run will be removed out of the call stack, and therefore you've got much more flexibility in your use of variables. Your code is much more stateless. It means that you can transfer subroutines from one program to another quite easily, and then within this we're using parameters and arguments to interface between this global and local environment. So Pascal and BASIC were basically the first languages to be procedural. So you can see here on the screen an example of something that's not structured. We can see this code here, it's got line numbers on the side. I think this might be BASIC, and then you'll see that in here it's got like if the len of A, as in what you just typed in to be, trying to find it, can't find it. Oh, do you want more stars A? If the len of it is 0, then go to 90, so that means do you want more stars? So it just keeps asking you if you want more stars, and then otherwise it goes back to 30 and loops up to the top. So it leads, this just gives you an infinite loop. You've got this go-to. You can see there immediately, it wasn't particularly easy for me to understand what was going on there. And then you see this language Pascal below. This shows the introduction of structured programming. We can see that we've got begin statements. The code is broken down into blocks. We've got these for loops. You start to see the use of arrays. So there's more. So we've got aggregated data types. And most importantly, you can imagine the code is kind of like being in a hierarchical format now, and there's no go-to statements in there. Moving forward, this is C++ in German, weirdly, and this would be called procedural programming because within here, as well as having a subroutine, the subroutine's got parameters. So we've got these parameters, they're subroutine is not actually being called. This is the default subroutine it goes to, but it states what's input and what's done, and also what's returned. And we've got this idea of the hardware needing to be updated to actually manage this movement of parameters and arguments between the global and local domain. Right, so some further improvements. So having procedures with parameters that are going in and out of them wasn't really enough, and it wasn't abstract enough because it didn't promote reuse of code. And so in the sort of 80s and 90s we moved over to object orientation, which is the way that most professional programmers work these days. Effectively, your procedures and your global variables within a program were encapsulated into this higher level of abstraction called classes, and they were now known as methods and attributes respectively. Classes can be instantiated into objects at runtime. So as you would create a class which would be like a template for a ball, and then during the running of the program, the ball might have methods like bounce and kick, and attributes like that it's red and how fast it can move. And then during runtime you could create multiple instances of these balls known as objects. That actually created a whole new dynamic to programming, because it meant that you could choose how many objects you wanted running within your program at once. With procedural programming you'd have to define all the data that you would need to use during the running of the program, and it meant that programming is much more flexible and more powerful, because you could do things like simulating complex environments like an ant farm or the spread of an epidemic through a population, and also to more 3D environments, which led on to improvements in computer games. Examples of good object-oriented languages would include Java and C++. On the other factor about object orientation is that when you define a new class, what you can do is you can inherit all the methods and attributes from previous classes, and that really promotes the reuse of code. So a paradigm that sort of exists within object orientation is known as event-driven programming, and this is principally used for the generation of programs which have a graphical user interface. So graphical user interface is what you're familiar with. It's any kind of interface that has windows, icons, menus and pointers. Event-driven programming is often implemented as by importing a library into a specific language. So for example, tkinter is the native GUI library for Python, and Swing is the native library for Java. Some languages developed as event-driven, kind of off the shelf, like VB.NET and C#, and they're kind of the whole thrust of them is that VB.NET, you're presented with a view in which you can drag and drop the buttons and forms together using a kind of what you see is what you get interface, and then when you double click on a button you can then go and proceed type in code for what happens when the user clicks that button. The principal way that it works is it has a main loop function that basically sits there and listens to events and triggers that are generated by the operating system, and then you supply it with callback functions to react to the events and triggers. So for example, a trigger might be a mouse click or a hover over something that will cause something to happen on the screen. And you shouldn't really narrow your understanding of event-driven just to graphical user interfaces, because they're also used in web scripting language and embedded systems. So for example, in a web scripting language it might be that a certain set of form data turns up, or an embedded system might be that a temperature sensor in a washing machine reaches a certain temperature. Okay, so I've got some examples. On the left is Java, I believe, and in here you can see that as well as having procedures, in here I believe they're procedures, they're not returning values. It's got 3 procedures, but they're all wrapped up into this larger thing called a class, and you don't actually see the class being instantiated into a method, but you get this idea that there's a higher level of abstraction within the program than just the procedures. So it's sort of like an extra layer to the hierarchy to help you organize your code. And then on the right we've got I think it's Visual Basic, and this here is event driven. So you can see the bit here is you've got your procedure. This is within a class, it's just been snipped away, and here we've got button load.click. So this is going to be triggered once this button is clicked, and they've got some code within that for helping it. And also you'll note that within it there's wide use of object orientation. So every time you see a dot, that means that that's calling a method from that object. So how do you put all these things together? Well, I think the kind of the parent paradigm is imperative, and then each of the other paradigms are sort of nested within that. So you could say that most event-driven programming is object orientation. All object orientation would be procedural by nature because it requires you to use parameters and arguments. Procedural programming is structured, and structured is imperative. So it's a kind of a nesting of, and also within this the imperative paradigm, you can see these as continual improvements and also a continual separation between the complexities of the hardware and actually solving the problem that the programmer needs to solve. And as you get closer to the event-driven programming, you're adding on more and more libraries and more compilers and translation software, so that your code that you're running is actually going to run slower because of this constant sort of translation and mediation by the translators and the operating system. Right, so the other side of the programming languages, as I talk, was declarative. So these ones of which you just express the logic of computation without actually describing its control flow. So all of the previous ones had sequence, selection, iteration in them, and none of these do. Well, they pragmatically, some of them do, but the thrust of the language is that you specify what you want it to do without telling it how you want it to do it. And so there's four ones. There's more than this, but these are sort of the popular ones that you'll come across in your early studies in computer science. That's functional programming, logic programming, regular expressions, and database query languages. So logic programming, this specifies rules, facts and rules. So the rules, if you look at this example, they've basically stated that the ways that you could be a parent of somebody, or I don't know what syscon means, but this is a kind of like a genealogy kind of database, and it's coming up with all these rules about whether you're someone's cousin or whether you're their father's father or their father's mother's. And then into this you would then go on and state rules. So for example, like Bob is X and Y would be replaced by name, so Bob is Richard's father or Jean is Richard's mother, and then you would know that if you were to type in Bob and Jean as the parents, it would tell you that Z was there, the child would be Richard, for example. And so you can then, so you state the facts and the rules, the facts being the actual specific people, and the rules being how you construct kind of genealogy, and then the computer has an inference engine that goes through this and determines which one of these actually need to be carried out, and that's logic programming. As you guessed, it's used mostly in AI. Okay, database queries language, you might be a little bit familiar with this from your early studies or any kind of web development stuff you've done. The key kind of global database query language is SQL or SQL. Effectively here what you're doing is you're stating which data structures, which facts you want out of a database, which tables they exist in, what the conditions are that you wish to extract data, and then how do you want these grouped by. And what this will do is it will go into a database file for you and extract the data that you need. It provides a layer of abstraction between you and the actual data structure. So because you're not telling it how to extract the data, it also allows the environment to be flexible enough for you to actually make changes to the data structure and then not have to go back and update your SQL wildly unless you change something that's pertinent to that SQL query. And so this is a querying language. Notice that you're specifying what you want out, not how you want to retrieve it. Functional programming, I'm told it's the next big thing. It's used in domains like maths and potentially kind of like machine learning, things like that, data mining. It's where you want to get through a lot of data really, really quickly. And you'll note here that again, you're not seeing if then else. It's specifying kind of in this side I believe this is F#, and you're specifying kind of data objects and how they relate to one another. And I believe here we're specifying functions, and this is Haskell. And so the result of which is it's super, super quick and can deal with really, really big data sets. Finally, regular expressions. I've read on a Wikipedia page that regular expressions were counted as a programming language. And I was like, aren't they more like HTML or something, which is a markup language? So HTML doesn't do any programming for me because it doesn't actually solve a problem. It just tells you what goes into a web page. And regular expressions for me are just like, they just tell you what the correct format a bit of a string should be. So in this one, this is Python, and the actual regular expression exists within this re.findAll. So re is regular expression, findAll is a function, and then you give the regular expression language, and basically this is saying, I believe, some number of characters followed by a dot, then an @ sign, and then one or more character after that with a dot in it, I believe. I'm not sure. And so within that, it's comparing each one of these to ABC, and it's going through this, and if it's an email, it gets transferred and it prints the email afterwards. I would say that probably the reason why this is a declarative language is because regular expressions are used in places like web searching, finding things, and replacing text. And so what you're actually doing is you're specifying the criteria to the solution of a problem, but you're not telling the computer how to carry it out. The actual the way that it's carried out is through the regex library in Python, but there's a regex library in most other languages. So I just went through the 4 parts of declarative languages, and we've talked a little bit about the imperative languages, and often there is just this divide and we think, right, imperative and declarative. Some courses in computer science also go through the idea of, they introduce the types of programming languages not through a division of their properties, but kind of on a timeline. And so I thought I'd go through that. And so these 1G, 2G, 3G, 4G, and 5G are reputedly the generations of programming language, starting in the 1950s, working forward into the 2000s. And it's basically, you can see the sort of subsequent improvement of programming languages, but most programming languages you work with at the moment are 3G. So in the 1940s and 50s, we had machine code. We used to program computers with punch cards, and it was binary instructions. Then we invented assembly code, which allowed the instructions to be human readable. So instead of ones and noughts, we were saying add and sub, and we produced this platform-specific code. The introduction of high-level languages and imperative programming meant that we could now compile programs onto specific devices, and that was the advent of third generation languages. And within that, you would probably also consider kind of object orientation to be kind of within the domain of third generation. And then, so often textbooks have first, second, and third generation. There are fourth and fifth generation. They don't really get as much discussion these days. Fourth generation are domain-specific languages. So they're languages that work for a specific type of problem and are largely meant to speed up the process. So you don't have to worry about the how so much. You just get on with specifying what you want. So, for example, SQL as a database management tool. So you might use SQL by opening up Microsoft Access and then dragging and dropping some queries and forms together. And then when you actually want to do the programming, you just go in and you specify, this is the data that I want out, and then you can put it on the screen the best way that you can. So that would be a fourth generation language. Web development, you're seeing more and more sophisticated use of web development frameworks, things like Django and Flask, that make it really, really quick to produce a website, and you're using templates, and so you're specifying you have to specify less of the actual how and more just kind of what you want to do. And also GUI development, so all of event driven programming. So the idea that you use a rapid application development tool